It's been a long while since I made a physics video, and in light of final season and some of my wonderful students going in to take their Physics 1 finals, I thought I would make a brief video going over what I believe is maybe the most prevalent concept in almost any physics course, especially in the MCAT, and that is work energy theory, the relationship between work and energy. And I could give a lecture on what work and energy specifically are, but given the fact that most of you have probably already taken a course and maybe have an explanation, I'd be more than happy to give my own explanation. I'm more focused on creating a repeatable thought process that you can use to actually solve these problems, right? That's the hardest part about physics is when you go into a problem, how to actually structure your mental framework such that you can come up with an answer. And a repeatable process to attack these sorts of problems, I think, is a very good grounding device. And so with that, I'm going to give you my recommendation for how to approach these types of problems. And so without further ado, let's get into it here. So this is how to solve any work energy theory problem. And the first step is to actually identify that you're going to be using work energy theory. So my first step here is there some source of potential or kinetic energy? K or U, basically. So this is under two assumptions, right? That energy is represented by some addition of a kinetic portion and a potential portion. We can have translational kinetic energy, we can have rotational energy, kinetic energy, we can have gravitational potential energy, we can have elastic potential energy. At least at this level of this course, these are the main ones that you're going to be dealing with. And more importantly is the actual work energy theory, which is basically saying that work is equal to change in energy. What does that mean explicitly? So if it basically is telling us that if something is doing work, if some force is doing work on a system, it will change the total amount of mechanical energy. There's this notion that energy cannot be created or destroyed, it can only be transformed, right? So it could be drawn out of the system in forms of heat via friction, which is going to be the most prevalent case in these levels of courses. But there's going to be a total change in the amount of energy that exists within a system. So once we identify that there is some source of potential, some source of kinetic energy maybe, then we write down this equation. This right here is the key. You write this at the top of any problem that has to deal with this work energy theory. And then from there, we can modify it by asking ourselves our second question. Are there any non-conservative forces acting on the system? And then in parentheses, I wrote force of friction. So force of friction is going to be the most prevalent one that you're going to deal with at this level, but a non-conservative force is basically a force that does not conserve the amount of mechanical energy in the system. And things like friction or drag can take away bits of energy. It doesn't destroy the energy, but it converts it into something else that is outside of the system. So if we look at a problem and it has friction, for example, we can basically write down that if there's friction in our problem, I'll phrase it that way, then the work is equal to, or represented by, that's what that 3 bar means, is represented by F times D times cosine theta. And F is the force that is doing the work, so in this case, friction. D is the distance that it acts for, so distance. And cosine theta is the cosine of the angle between the distance vector, or the direction of motion, and the force vector, the direction of the force, right? Otherwise, if there are no non-conservative forces, then the amount of work being done on the system is equal to 0. And this is a unique case where we have what we call conservation of energy, or COE. And this happens when change in energy at any 2 points is equal to 0. Well, what is change in energy? It's the minus the initial energy. So from that, we can just move the initial energy to the other side of the equation, and we get that EI is equal to E, right? These are composed of different elements. One instance might have more kinetic or potential energy than the other, but the total amount of mechanical energy, the total magnitude in joules, will be the same, All right, so again, we are determining that we need to use work energy theory. We have some source of potential or kinetic energy. Then we ask ourselves, are there non-conservative forces? Basically, are we going to include work in the system? And then the third part is just determining our equations and our variables, right? So we already have this equation for work up here. And then it's up to us to determine what the energy is represented by in those specific instances. So EI will be equal to what? EF will be equal to what? And we have this general formula that energy will be equal to some kinetic plus some potential component. And then we have to plug everything in, right? All we do is work is equal to EF minus EI. And whatever we determine those specific variables to be, we can then extract what we need out of the equation. So once again, we are determining that we need to use work energy theory. We are asking ourselves if there are any non-conservative forces, and then we are figuring out our equations and variables for energy and for work, and then we just plug everything in and we extract a variable that we're asked for. So let's do an example. So a very common example has to do with an incline. And let's do a problem here where we have a box on a slope and we're asked to find its final velocity when it reaches the ground. And let's say this is at some angle theta. And right away, we'll ask ourselves that you can do Newtonian mechanics here too, but there's an easier way with energy. So right now, this box is at some height h. And what's our first question? Is there some source of potential or of kinetic energy? And yes, there is. So 1, yes. We have Ke at bottom, right? Because we're asked about the velocity. And we have potential of gravity at the top when it's at the top of the slope. So from there, we do our first step. I'm going to put a big red star that work is equal to change in energy. Perfect. Now let's see. Question 2, are there any non-conservative forces acting on the system? Well, in our instance here, we're going to say that this is a frictionless surface. So if there's no friction, then from there, we can determine that work is equal to 0. No friction. Wonderful. All right. The next part is then determining our equations. So we have EI is equal to what? So EI is going to be Ki plus Ui, right? Plus the initial potential energy. And what initial kinetic energy do we have? We have nothing, right? It's not moving. So this will be 0. And our initial potential energy, well, that's just the gravitational potential energy, which has an equation of mgh. Wonderful. All right. EF would be equal to Kf plus Uf. Well, at the bottom of the slope, when we're here, what's our potential energy? It's nothing, right? Because the height is 0. We have no gravitational potential energy, so this will be 0. And we'll just be left with the kinetic turn of 1/2 m, I'll call it V final squared. And now we can set up our equation, right? Work is equal to 0. So let me write everything out. Work is equal to EF minus EI, or work is equal to 0. Work is equal to 0, which is equal to EF minus EI. So we can say conservation of energy. And we have, therefore, that EI is equal to EF. And we can keep going. EF we determined was 1/2 mv squared. And EI we determined to be mgh. And now we have an equation that we can use to determine the variable we're looking for, which is the final velocity of the block. So we can cancel these m's off of both sides. This 2 can go over to the other side, and we'll be left that the velocity will just be equal to the square root of 2gh, which is a very common answer. This is a very typical physics problem. All right. So now let's see if we can make this a little bit harder. So let's do the same thing, but let's ramp it up quite a bit. So let's say that we have the same instance, but now we have some angle theta, some distance d, some collapse here in the spring, delta x, and some coefficient of friction on the incline, mu. So I added quite a few things. I'm basically building a mousetrap right now, but we can do it. right? So there's a few things that we need to determine. The crux of this problem is to determine how much the spring is compressed by. Delta X is equal to what? And it may come as a surprise, but we can use our same methodology here in order to determine what this variable is. So let's do it. We need to find the compression of this spring. So if we start from this instance, we're going to have a few different instances, I guess. We're going to have, I'll call them A, B, and C, where the spring has been compressed from equilibrium, some maximum amount, delta X. And let's take the snapshot from B to C. So let's do this. So B to C snapshot. Let's undergo our same process. So here, are we going to use work energy theory? Well, yes, we are. We have some source of potential and some source of kinetic energy. We know that the block is going to be moving at some speed here. It's going to have this kinetic energy, this translational kinetic energy when it's moving from the bottom of the slope to the spring. And it's going to have some elastic potential energy when the spring is compressed. So yes, we are going to use work is equal to delta E. Again, every problem we're writing work is equal to delta E. And now, for part 2, in the snapshot of B to C in this specific moment, are there any non-conservative forces? I'll give you a moment to think about that, but the answer is no, there's not, right? From this point, from the bottom of the slope to the spring, there are no non-conservative forces. Friction only exists on the incline, right? So we can say here that work is equal to 0, all right? And then in part 3, we need to determine what our energies are, right? So E is equal to K plus U, and we can go on and say that EI, or I'll say EB will be our initial instance, will be equal to this 1/2 mv squared, right? And EC will be equal to, well, only elastic potential energy, which is equal to 1/2 K delta X squared. And that K is the spring constant of the spring. So now we have an actual problem here. We have 1/2 mv squared is equal to 1/2 K delta X squared. We can cancel these, and we get that delta X will be equal to the square root of m over k times v, which is an okay answer, but let's say you can't answer in terms of v, which is pretty common in physics. You don't know what the final velocity is of the block when it reaches the bottom of the incline. So it's up to us to actually come up with some answer here. This is, again, I kind of cut forward and did step 4. This is EF equals EI. So now let's do the other snapshot. Let's do from A to B. And in this instance, we have the block at the top of the incline moving down to the bottom of the incline. So are we going to use work energy theory? Yes. So step 1, work is equal to delta E. Step 2, are there any non-conservative forces? Well, in this regime, there are. We have friction. We have this coefficient of friction mu. So we have to define work is equal to force times distance times cosine theta. And now comes, I guess, maybe the hardest part of this problem, which is defining all of these instances in work. So this force is equal to the force of friction. The distance that it travels is d, and this cosine theta will be the theta between F and D. I also want to correct something on the problem. I'm sorry if you've already written it down this way. But let's say that it only gave you some height, call it h naught, all right? So now it's up to us to determine these factors. Well, force of friction can be represented by, if you recall from your Newtonian mechanics, mu times the normal force, right? And if we did some blow up here, we had our box, and this is our force of gravity, mg. Well, there is a parallel mg sine theta component and a perpendicular mg cosine theta component. And the perpendicular component will be equal to mg cosine theta minus the normal force, which is equal to 0, right? It's equal to 0 because it's not accelerating in the perpendicular direction. The block is not flying off of the incline, nor is it seeping into it. And so we have these two forces that are perfectly counterbalancing one another. So we can just basically say that the normal force will be equal to mg, I'll call it alpha, just so we don't mix it up with theta for our work equation. So let's say that this is some angle alpha. Sorry to backtrack here, guys. All right, so normal force is equal to mg cosine alpha. D is this distance, and we can actually determine this distance with just trigonometry. So sine alpha will be equal to the opposite side, which is h naught, over the hypotenuse. Well, the hypotenuse is the distance that the block travels, h naught over d. So we can then say that d, or the distance that it travels, is equal to h naught over sine alpha. Perfect. And last but not least, we have cosine theta. In this example over here, I'm going to zoom in just so we can maybe see it a little bit better. We have the force of friction here and the velocity going down the incline. So what's that angle? That's an 180-degree angle. So the direction of motion and the direction of the force of friction is always 180 degrees. So cosine 180 degrees will be equal to -1. So now we can write all of this in. So force of friction will be equal to mu times mg cosine alpha, right? Because mu times the normal force. D, the distance, was equal to h naught over sine alpha. So we can write work is equal to mu mg cosine alpha times h naught over sine alpha times -1, which would give us mu mg h naught. Cosine over sine will give us cotangent alpha, and then times -1, I'm just going to put a negative right up front. And there, we did it. We solved for the work. I know it was difficult, but not too crazy, right? So this is our answer for the work. And now we can solve for EI and EF. So EI is our initial energy. Well, initially, we're at the top of the incline, and we just have gravitational potential energy. So EI will be equal to mgh. F will be equal to 1/2 mv squared. And there we have it. That's that velocity that we're looking for in order to plug it back in to our initial equation up here, right? That's what we're solving for. So let's keep going. We're almost there. So now we have to set up the whole equation, right? That work is equal to EF minus EI. So therefore, we have minus mu mg h naught cotangent alpha will be equal to 1/2 mv squared minus mgh. It also makes sense that work is negative because friction would be taking out mechanical energy from the system and converting it into heat. So good thing that we see a negative sign here. And now we can just solve for v squared. This is what we're looking for. So m is gone, m is gone, m is gone. The 2 can be gone. I'll just put a 2 here and here. And we finally end up with, I'll write it down here. Hopefully you can see that V is equal to 2g h naught 1 minus mu cotangent alpha. So therefore, V will be equal to the square root of 2g h naught 1 minus cotangent alpha. Woo! What a workload. But we're not done. We need to figure out what delta x is, right? So as our callback, because delta x would be equal to square root of m over k, v, it would then be equal to square root of 2gm h naught 1 minus cotangent alpha over k. And we solved for exactly what we wanted to do using our method described in the beginning. So last recap. Is there some source of potential? Yes. We write down the boxed equation, work is equal to delta E. Then we identify if there are any non-conservative forces, most importantly friction, especially at this level of the course. Is there friction? If yes, we need to fill out the work equation, what it literally means to have force, distance, and the angle between them. And if no, then we can use conservation of energy, just that the initial energy at some instance is equal to the final energy at some other instance. It will always be the same in magnitude, not necessarily in what it's composed of, but composed of, but of magnitude. And last but not least, determining our equations and our variables. So what our initial energy is composed of, what our final energy is composed of, and then plugging it all in. And then from there, we can determine whatever variable the problem is looking for. So even if you don't make it all the way, you'll be able to write down all these different equations and hopefully come to a answer and be able to get some credit. So thank you for taking the time to listen to me. If you have any questions at all, please feel free to leave a comment. I'm aiming to do maybe some physics info answering sessions, but it really brings me a lot of joy to explain this stuff to you. So if you're receptive, I would be more than happy to do more things in the future. So take care, everybody. I'll talk to you very soon. Thanks again.